Hey everyone, welcome back.
Hi.
So today we're going to be taking a deep dive into something pretty mind-blowing.
Yeah.
AI being used to solve some of the toughest math problems out there.
Oh, really hard ones.
Yeah, the ones that have like stumped mathematicians for ages.
Absolute.
Problems so complex they were basically considered unsolvable by computers. Until now.
Yeah, until now.
It's pretty wild.
It really is a huge leap forward.
I can't even imagine like a computer
In the
Augmented.
field of automated theorem proving,
Yeah.
we're seeing AI tackle challenges that were once thought to be exclusively
only humans could.
the realm of human ingenuity.
Wow.
Right?
That's crazy.
Guys.
So the research paper that we're looking at today is called
a deep dive.
Solving Hard Mizar Problems with Instantiation and Strategy Invention, which is kind of a mouthful.
It is a bit of a mouthful, but
Don't worry.
we're going to break it all down.
Descriptive title.
Yeah.
It tells you exactly what they did in the paper.
Oh, exact.
So the research focuses on
So what is this?
the Mizar Mathematical Library,
Mizar Mathematical Library.
which is like a massive digital library
Oh, okay.
of theorems and proofs.
Like a database.
Yeah, like a giant database.
Okay.
And it's one of the oldest and largest collections
Wow.
of formally verified mathematics.
So it's been around for a while.
It has been around for decades.
Wow.
And it's been a testing ground for automated theorem proving systems for decades.
Okay, so this Mizar library is like the ultimate proving ground for AI.
Yes.
That wants to like flex its mathematical muscles.
Absolutely.
Right.
Yeah.
But you said that even the most advanced systems could only solve about 75% of the problems
Correct.
in this library.
Yeah.
So what makes that remaining 25% so difficult?
So the remaining problems often involve complex logical structures, intricate relationships between different mathematical concepts,
Oh, wow.
and a level of abstraction
Okay.
that makes them incredibly difficult
Right.
for traditional automated theorem provers to handle.
So they're like really abstract.
Yes, very abstract.
Okay.
It's like trying to navigate a maze
Oh.
with countless twists and turns and dead ends and hidden passages.
Oh, okay. I'm starting to see why these problems are such a challenge.
Yeah, they're really tricky.
So how did this research manage to kind of crack the code,
So
so to speak?
the researchers introduced two AI systems,
Oh.
CVC5 and Grackle.
Oh, okay. CVC5.
Yes.
Okay.
CVC5 is what's known as an SMT solver,
SMT solver.
which stands for Satisfiability Modulo Theories.
Okay.
Now, instead of trying to prove a theorem in its abstract form,
Oh.
CVC5 uses a clever technique called instantiation.
Instantiation.
So it creates specific examples
Okay.
and sees if they hold true.
Okay, so instead of trying to prove that like all triangles have certain properties,
Right.
it would be like, let's make a right triangle
Yeah.
with these specific side length
Exactly.
and see if it holds up.
Exactly.
Exactly.
In that particular case.
Yes, and by testing a bunch of these specific examples,
Okay.
CVC5 can build up evidence to support the general theorem. It's a very powerful way to navigate that complex maze
Right.
we were talking about,
Yeah.
focusing on concrete paths.
Right. Instead of getting lost in the abstract.
Instead of getting lost in the abstract, yeah.
Okay. That makes a lot of sense.
Yeah,
But CVC5 doesn't work alone.
it does not work alone.
Right. You mentioned another AI system
Yes.
called Grackle.
Grackle, right?
So what does Grackle do?
Grackle acts as a strategy coach for CVC5.
Oh, okay.
Think of it as a chess grandmaster,
Okay.
analyzing the board and suggesting the best moves.
Okay.
So Grackle figures out the optimal settings and tactics for CVC5 to use on these tough Mizar problems, guiding it toward the most promising paths to a solution.
Oh, so it's like a dynamic duo.
Yes.
Like Batman and Robin.
Yeah, exactly.
Dynamic duo.
The brawn of CVC5
Yes.
combined with the strategic brilliance
The strategic mind
of Grackle.
of Grackle. That's right.
Okay, cool. What kind of results did they see with this approach?
So the combination of CVC5 and Grackle
Okay.
was able to solve over 3,000
3,000.
Mizar problems
Wow.
that were previously considered unsolvable,
Wow, that's huge.
which boosted the total number of solved problems to over 80%,
80%. That's it.
which is a massive jump.
That's a game changer.
It is.
Like, that's a big jump.
It is a huge jump.
That's crazy.
Yeah.
Okay, but how did they actually do it? What were some of the specific techniques they used?
One key technique
Yeah.
they highlight in the paper
Huh?
is trigger selection
Trigger selection.
And it helps CVC5 focus on the most relevant parts of a problem.
Oh, okay.
Avoiding unnecessary detours and dead ends.
Oh, okay.
In the search for proof.
But it's like giving it a roadmap.
Exactly, gives it a roadmap.
Okay.
To help it navigate the complexities of the problem more efficiently.
Cool, but can you give us an example?
Like
a concrete example?
Yeah.
Of how this all works in practice?
Absolutely.
Because we're talking about solving, like, really hard math problems here. I need to, like, wrap my head around it.
So one example they mention is related to Kuratowski's closure complement problem.
Kuratowski's closure complement problem.
A classic puzzle in the field of topology.
Okay, so already I'm lost. Okay, so
topology. I don't need to know what that is.
So topology is a branch of mathematics that deals with shapes and spaces.
Okay.
And how they can be deformed without tearing or gluing.
Okay.
Now this problem deals with how many different sets you can create by repeatedly applying the operations of closure and complement to a starting set.
Wait, hold on. Can you break that down a bit?
Sure.
What do you mean by
closure and complement?
Imagine you have a set of points on a map.
Okay.
The closure of that set would include all the points within the set as well as all the points on its boundary.
Oh, okay.
The complement would be all the points on the map that are not in the original set.
Okay, so everything outside of it.
Everything outside of it, yeah.
Okay, I think I'm following. So Kuratowski's problem is like if you take a set and you keep applying these two operations. How many distinct sets can you generate?
Exactly. And it turns out that the answer is 14.
14.
Which is kind of surprising.
Really? Only 14?
There's this hidden structure.
Wow.
This limit to how much you can expand a set using these operations.
That's so cool.
It is.
Okay, so what did CVC5 actually prove?
So CVC5 tackled
about this problem.
A theorem related to a specific family of 14 sets derived from these operations. It's successfully proved that this family is already closed under both complement and closure.
So you can't.
So if you apply those operations to any set in this family,
you won't create new sets.
You won't create any new sets outside of that family.
Okay.
Yeah.
So it's like a closed loop.
It's a closed loop. Yeah.
Okay.
So it confirmed a fundamental property of this set family.
Right.
Which is a pretty significant contribution.
Yeah.
To our understanding of Kuratowski's problem.
Oh, wow. So it like helped us understand this problem.
It did.
Better.
Yeah. And it highlights how CVC5, guided by trigger selection and Grackel's strategic advice, can tackle these complex mathematical concepts and contribute to solving long-standing problems.
That's amazing.
It is.
This is all incredibly fascinating.
It is.
But I have to admit, it's a lot to wrap my head around.
I know it's a lot.
I think we need to take a break.
Yeah.
And we'll come back.
Let's take a break.
And dig a little deeper into how these AI systems are actually pulling this off.
Okay.
So buckle up, everyone, because in part two of this deep dive,
we'll unravel.
We're going to be unraveling
more of the secrets.
More of the secrets behind CVC5 and Grackel success.
That's right.
We'll explore more examples of the problems they've solved.
Yes.
And delve into some of the other techniques that make their approach so groundbreaking.
That make it so groundbreaking.
All right, see you soon.
See you in part 2. Welcome back.
All right, so last time we left off with CVC5 and Grackel successfully tackling some pretty tough math problems.
Yeah.
And I'm really curious to learn more about this instantiation technique.
Yeah.
It sounds almost too simple, like creating specific examples to prove general mathematical truths.
Right.
How does that actually work?
It's a great question.
Yeah.
And it gets to the heart of how these AI systems approach problem solving. So instantiation allows CVC5 to explore a vast landscape of possibilities more efficiently.
Okay.
Think of it this way.
Yep.
Instead of trying to understand the entire universe at once, CVC5 zooms in on specific galaxies, stars, and planets, studying them in detail to gain insights about the universe as a whole.
Okay, so it's like breaking down a complex problem into smaller, more manageable pieces that the AI can actually grasp.
Yeah.
But how does CVC5 know which examples to choose?
Right.
They can't just randomly pick and choose, right?
You're absolutely right. You can't just randomly pick and choose.
Yeah.
That's where Grackel, the strategy coach, comes into play.
Okay.
So Grackel analyzes the problem.
Yeah.
learns from past successes and failures,
Okay.
and advises CVC5 on which instantiation techniques are most likely to be effective.
Okay, so it's like a seasoned explorer.
Yeah.
Guiding CVC5 through uncharted territory.
Exactly.
Pointing out the most promising paths to follow.
That's a great analogy.
Yeah.
Yeah. So Grackle is constantly learning and adapting.
Okay, cool.
Refining its strategies based on experience.
That's pretty remarkable.
It is.
We talked about Kuratowski's closure complement problem last time.
You did.
Can we revisit that example and see how instantiation played a role in solving it?
Of course. So remember, Kuratowski's problem involves repeatedly applying the closure and complement operations to a set and seeing how many distinct sets you can generate.
Right.
And the surprising answer is 14.
14.
Yeah.
It's like there's this hidden structure, this limit to how much you can expand a set.
Right.
Using these operations.
Yeah, exactly.
Okay.
Now, instead of trying to prove this general property for all possible sets, CVC5 guided by Grackle might start by focusing on a specific set.
Okay.
Say the set of all points inside a square.
All right, a square.
It would then apply the closure and complement operations to this square repeatedly.
Okay.
And observe the results.
So it's like running a simulation.
It is like running a simulation.
Yeah.
Seeing how the square transforms under these operations.
Cool.
And by analyzing the patterns that emerge from these specific examples, CVC5 can start to formulate conjectures about the general behavior of sets under closure and complement.
Okay.
It's like a detective gathering clues from individual cases.
Oh, that's a great analogy.
To build a broader understanding of a criminal's modus operandi.
Yeah.
Right.
So by studying these concrete examples, CVC5 can start to piece together the underlying principles that govern the more abstract mathematical concepts.
Precisely. And this approach proved to be very effective.
Yeah.
Remember how we said CVC5 proved that a specific family of 14 sets is already closed under complement and closure?
Right.
Well, this insight was likely derived from studying numerous concrete examples, like the one with the square. By observing how these specific sets behaved under the operations, CVC5 could generalize its findings to the broader family of 14 sets.
So it's like the AI is learning by doing, building up its understanding through experimentation and observation.
Precisely. And this experiential learning process is a key part of what makes CVC5 and Grackle so powerful.
Cool.
They don't just rely on pre-programmed rules and logic.
Right.
They can adapt and refine their strategies based on the problems they encounter.
That's incredible.
It is.
Now, besides Kuratowski's problem, you also mentioned that CVC5 tackled a theorem related to big O notation, a concept used to compare the efficiency of algorithms.
That's right.
Can you walk us through that example as well?
Certainly. So big O notation is a way to describe how the runtime of an algorithm scales with the size of the input. So essentially it tells you how much longer an algorithm takes to run as the input data gets larger.
Okay, so a more efficient algorithm would have a better big O notation.
That's right.
Meaning it can handle larger and larger problems without slowing down too much.
Precisely.
Okay, cool.
Now the theorem that CVC5 tackled involved proving that two specific mathematical functions were not in the big O relation with each other. This means their growth rates. How they scale with increasing input are fundamentally different.
Okay, but how did CVC5 go about proving that? Did it use instantiation in this case as well?
It did use instantiation.
Okay.
But instead of dealing with abstract functions directly, CVC5 likely generated concrete data points for each function. So it might have plugged in a series of input values like 110, 100, 1000, and so on. And calculated the corresponding output for both functions.
So it's like plotting points on a graph.
Exactly.
To visualize how each function behaves.
Yes, and by analyzing the trends in these concrete data points, CVC5 could discern the underlying growth patterns of each function. If the functions were in the big O relation, their data points would exhibit a certain relationship. Like one always being larger than the other after a certain point.
But if the data points didn't follow that pattern, it would indicate that the functions have fundamentally different growth rates.
Precisely.
Okay.
And that's likely how CVC5 was able to prove that those two functions were not in the big O relation.
Cool.
It used concrete data points generated through instantiation
Yeah.
to draw conclusions
Okay.
about the abstract relationship between the functions.
This is fascinating.
It is.
It seems like instantiation is a really powerful technique.
It is.
For bridging the gap between these abstract mathematical concepts and the concrete examples that AI systems can actually work with.
Absolutely. And it's one of the key ingredients in CVC5 and Grackle's success. But there's another somewhat unexpected factor that played a crucial role in their ability to solve these hard Mizar problems.
Okay, I'm intrigued.
And that's what we'll delve into next.
All right, I can't wait to hear about this mysterious factor.
All right, let's do it.
Welcome back for the final part of our deep dive.
Okay.
I'm ready to hear about that mysterious factor you mentioned.
Right.
That helped CVC5 and Grackle solve these incredibly difficult math problems.
It might surprise you.
Okay.
But one crucial element was the way the problems were presented to the AI.
Oh, okay.
So the researchers focused on converting the problems into a simplified logical form called clausal normal form.
Clausal normal form.
Or CNF for short.
CNF, okay.
So it's not just about the mathematical content itself, but also about how that content is structured and presented to the AI.
So it's like how we communicate with the AI.
Exactly. It matters.
Yeah.
Think of it this way.
Okay.
If you were trying to explain a complex idea to someone,
you
wouldn't just throw a jumble of words at them. You'd organize your thoughts. Use clear language. And structure your explanation in a way that's easy to follow. Right?
I'd understand.
That's essentially what clausal normal form does for mathematical statements. It transforms them into a structured format that's easier for the AI to process and reason about.
So it's like translating a complex mathematical idea into a language that the AI can understand more fluently.
That's a great analogy.
And
it turns out that this translation process, this conversion to CNF, can significantly impact how well CVC5 performs.
Really?
So certain clausal forms make it easier for CVC5 to identify promising instantiation candidates.
Right. Those specific examples we talked about?
Exactly. Other forms might lead to dead ends or make the problem unnecessarily complex.
So it's all about finding the right way
to
express these ideas. So choosing the right clausal form is like setting the stage for success.
Exactly.
Giving CVC5 the best chance of finding a proof efficiently.
Precisely. It's another example of how strategy and careful preparation play a crucial role in this whole process.
It's not just like brute force computation.
No, it's not just brute force. It's about presenting the problem to the AI in a way that makes its reasoning process more effective.
This really highlights the importance of understanding the interplay between mathematical content, logical representation, and the AI's reasoning mechanisms.
Absolutely.
It's like a delicate dance.
It is a delicate dance between human ingenuity and artificial intelligence.
And it speaks to the broader implications of this research.
It does.
Like, we're not just talking about solving a few math problems here. We're talking about the potential of AI to transform how we approach mathematics as a whole.
Exactly.
And that's what I find so exciting about this.
Yeah, me too.
So what does it all mean? What are the implications of having AI that can tackle these kinds of challenges?
The implications are far-reaching. So imagine AI systems collaborating with human mathematicians. Exploring new areas of mathematics. Discovering hidden patterns. And perhaps even proving theorems that have eluded humans for centuries.
It's like having a team of tireless research assistants working alongside you, constantly generating new ideas and pushing the boundaries of knowledge.
That's a great way to put it.
It's like a glimpse into a future where the line between human and artificial intelligence blurs, leading to unprecedented advances in our understanding of the universe.
Absolutely.
That's awesome.
And these advances won't be confined to just pure mathematics. Fields like physics, engineering, computer science, economics, even medicine rely heavily on mathematical models and theorems.
Yeah, that's true.
So progress in automated theorem proving could have a ripple effect across all these disciplines. Accelerating scientific discovery and technological innovation.
That's amazing.
It is pretty amazing.
This deep dive has been an incredible journey.
It has.
We've covered a lot of ground.
We've gone from instantiation and trigger selection to clausal normal form and the broader implications of AI in mathematics.
It's been a fascinating exploration of how AI is pushing the boundaries of what's possible in the world of mathematics.
It's a really exciting time to be following this field.
And that's a wrap on this episode of The Deep Dive.
Thanks for joining us.
I hope you've enjoyed exploring the fascinating world of AI-powered mathematics with us.
It's been a pleasure.
Until next time.
See you next time.
Keep those minds curious. Keep learning. And remember, there's always more to discover.